from the Columbia University. Please.
Thank you, and thank you all for being here after lunch. It's always a critical moment in the day, and thank you for the invitation. So today, continuing with the theme of today's lectures, we're talking a bit about random graphs and some connections to other parts of applied probability, something we like to call fixed point equations or stochastic fixed point equations. And I'll have a little queuing connection that I want to mention briefly at the very end. So if you bear with me, we'll get there eventually. Usually what I like to do at the beginning of my talks is to try to motivate why is it that I keep working on off the beaten path on something that not that many people seem to care about. So let me talk about why I consider ranking to be such an important problem. I am married to a consultant, and it's funny that I get exposed to lots of interesting ideas of where people are just trying to use information in whatever possible way they can. And we do live in a time where information is abundant, it's massive, it's everywhere. Everybody's measuring things that you wouldn't even imagine. The example that I want to bring up here in this talk is related to healthcare. In the American system, there are databases out there that know every single time any of us got sick, any single time any of us got a prescription. They can follow up every time we go to see the doctor, what doctors, what specialties, how we're using all that insurance that we pay for. And they, of course, the other side, the marketing side, is always trying to use this data to do something, to know who to target, who to sell to, what products are going to sell, what product, how should they be marketed. So in that sense, there's many places outside of the traditional things that we might have in mind where we have information that we want to organize. Organizing can mean many things to many different people, but I'm going to talk about ranking them. Ranking the information in such a way that makes sense for some specific purpose that we might have in mind. In particular, probably the most famous of all the examples, and the one that got me started on this line of work, is just thinking about the World Wide Web. Web pages, the internet. And we want to think about trying to organize these billions of web pages that are out there in some way that makes sense. Basically, what I'm talking about is how does your web search engine know in which order to show you the results to a certain keyword search? So if I type Newton Institute, is it going to show up at the very top? Is it going to show up, 10 pages after? What's going to determine in what order they appear? And that is happening through an algorithm that basically is ranking the pages. Right now, I guess, by far the biggest company in terms of search engines is, to this date, Google. Bing, that's Microsoft's competition, is trying hard, right? Trying hard to come up with something better. And I'll explain also why there is a need for something better. Yahoo, well, they're still doing a lot of things. Probably none of us still use it as our main web search engine, but it's out there. And there might be other search engines out there that are using different ways of organizing information. Now, to me, information is going to be the kind of information that we can use to construct a graph, that we can encode into some kind of graph. Graphs where we have nodes and edges and potentially extra pieces of information, which I'm going to call node attributes. I'll give you some examples. So, for example, the Twitter graph. The nodes would be the people. The edges would be the directions, who is following who. Probably not everybody has a Twitter account. I certainly don't. But it's an interesting topic. There are lots of people I know who are interested in trying to analyze what's going on with Twitter and figuring out why Kim Kardashian seems to have so many followers. If you don't know who she is, congratulations. The example that I was mentioning, healthcare networks, as I said, that's the one I'm exposed via marital relationships. And it's funny that there really is such a big amount of information out there, partly because everything has to be recorded. And there are companies that make a living out of collecting this information and selling it to whoever wants to purchase it. And there's so much out there that you can construct at least 20, 30 different kinds of graphs depending on what you want to include and what you want to represent. One example that I have in mind right now that I'm trying to work on is a graph where we're thinking about the nodes as being physicians. The edges can correspond to referrals, patient referrals between physicians. Why are we interested in this? That means that we're looking for physicians who are connected to many other physicians. And usually what's happening is that we have two classes of doctors. General practitioners, PCPs as we call them in the US, and specialists. What happens in a typical day? The PCP is the one who sees you on a regular basis. And let's say I go and walk in and say I have a heart murmur. So what's he going to do, or she going to do? Going to send me probably to see the cardiologist. The cardiologist is a specialist, sees in general a smaller perhaps volume of patients, and is going to probably prescribe something, some drug. And then he or she is going to refer me back to my PCP, and I'll go back, and then the PCP will keep on giving me the prescription and taking care of the evolution of my life in general. But what's happening at the same time? Well, whatever is that the specialist prescribed is likely to have an effect on all the people around. Why? My PCP is gonna look at what I got prescribed, and he or she might have other patients with a similar condition as mine. And say, well, if the specialist who I sent, who's potentially from, Mass General or some, fancy, fancy hospital with lots of credentials, I'm not gonna, if he or she said that I should give Lipitor to this person, well, let's do the same to all my other similar patients. So there's a cascading effect. So who are they looking for? They're looking to identify those doctors who, once they adopt a certain therapy or a certain, drug, will have an influence, a broad influence, on other doctors who will continue doing the same. And there are similar examples in other areas as well, where the interest is sometimes to find these people. And it's not as trivial as finding the doctors that have the largest volumes of patients. As a matter of fact, sometimes they're not. Sometimes they're very, very specific, and they limit the volume of patients that they themselves see. And they will not take referrals for just anybody. They will probably take referrals only from a handful of people. But still, their level of influence can be very big when you compare it to the larger size of the population. So that's one example besides the famous internet and web page ranking that I wanted to mention, because I think there's a lot of room for other kind of problems that are outside of just ranking the internet. Another one, as we already heard talk about, Amy mentioned the citations, and we all review papers. We all are probably concerned to some extent about citations and stuff people use ranking algorithms to try to identify who wrote the important or relevant or innovative papers. And again, it may or may not be the case that those original papers, seminal papers, are cited directly a lot. They may, many times they are, sometimes they're not. Typical examples is when the first paper is so poorly written because it was so complicated, it was still sort of immature, it's a brilliant idea, but it takes about 2 or 3 other people to translate it to Common English. Who gets cited? The Common English version, usually. So what happens in those cases? Well, if I'm really looking for who's the one who originated the brilliant idea, it might not be so trivial to find it. Why? Well, if I count only the immediate citations of that hard-to-read paper, I'm not going to get a high rank, let's say. But if I start looking at the overall rank of, let's say, the people who cited it in the first or second generation, I might actually see a lot. And it does happen. I think if you look up Loin's paper on stability of Qs, there's a couple of his citations that have way more orders of magnitude more than the original paper. Just a cute little example. Anyway, so we also heard a talk earlier today when we mentioned the Yelp customer review side, where people are offering their reviews of many different businesses and services in general. It comes in very handy for especially people who, if you're looking in New York for one FedEx office where you're not going to have to wait and you're not going to have to fight everybody, well, that's a good way to identify which one you should go to. And again, there's a lot of information that is available. There are many situations. Amazon internally ranks, again, its reviewers and its products in different ways. So there are many graphs that one can construct also in that case. As I said before, I'm interested in representing the information in the form of graphs where we have nodes, edges, and in my case, node attributes. I'm not going to talk too much about potentially edges that can be weighted, like where there's information between the nodes that can be encoded into the edge, because as of right now I haven't worked on any of that, but I do add in some sense, something about node attributes, which goes a little bit beyond what Google's original idea started with. And I'll explain that in a few minutes. My point with these examples is basically to give you the message that there are different problems that lead to different types of graphs that might lead to the need of different ranking schemes. There's not a one solution fits everybody, which means we probably do want to have a way of figuring out different algorithms, customized algorithms for that will have different properties. Now, when I talk about typical, different graphs, I wanted to show you a picture of some, just to give you an idea of different. These are all sort of real. This is a synthetic graph, power law graph. You can see, some nodes are very heavily connected. It's fairly sparse. This is a very, very, very famous depiction of the internet at the router level. So famous that it's part of the MoMA's Museum of Modern Art, Metropolitan Museum of Modern Art in New York collection, and it's very pretty. This is an undirected graph, all of the ones I put here. This I found also while browsing the internet. It's a depiction of the link structure within the Amazon website. So it's also fairly nice and cute the way that they drew it. Again, we have some parts of the website that are extremely heavily connected, even though they're sort of at the edges. So we can see some sort of what we would call scale-free behavior there. What these graphs have in common is those big stars or hubs. Some nodes are very, very heavily connected. And what does that mean in terms of what we do? That usually, to somebody like me who has been working on heavy tails all her life, means there are heavy tails in there. Why? Because if I look at those nodes with lots of neighbors, yeah, there's sort of few, but not as few as you would think. So that's sort of how I got started on this, because it sounded like, well, there has to be something in there, and let's try to find what it is. Here's a little bit of what the problem is and how these heavy tails are going to show up. What I want to analyze is what I refer to as the typical behavior of the algorithm. Just don't get me wrong. It's not that I don't think that just finding the numbers themselves is useful. Actually, somebody has to find those numbers. And there are many methods that can be used to do that. But I'm not interested in computing the ranks. What I'm interested is in trying to understand what is the algorithm doing. Which nodes are getting more importance in the ranking? Which nodes are going to be highly ranked? Can we characterize those nodes? Can we say, oh, it seems that if a node is going to be very highly ranked, it's because of this? What's the mechanism in which it's happening? That is not related to actually computing the numbers themselves. That's a whole different problem, which has another side and a whole set of problems or technical problems related to that. But I'm not going to go into that direction. What I'm interested is in qualitatively being able to say something about who is being benefited by the algorithm. Also because I have in mind this idea that we want to be able to customize the ranking in the sense that if I want certain types of nodes to be highly ranked, let's say those physicians, specialists that can reach lots of general practitioners in a short amount of connections, then I'm looking for something else than just the immediate number of connections. So it can be different for different problems. Can we determine the distribution of the ranks? Again, without actually computing the ranks. I don't want to have to compute any kind of algorithm on a million or billion nodes graph. That's just going to take me too much time just to get a whole bunch of numbers, which may or may not tell me anything about who they are. And also, I want to be able to use this kind of theory to be able to say, well, if you do this, if you include this information, then what's going to happen is that the algorithm is going to behave this or that way, and it somehow is connected to what is it that I'm measuring. So if I can use these analysis, this theoretical analysis about the algorithm to tell me which pages are being benefited or which nodes are being benefited, then I could sort of engineer it, reverse engineer it to obtain an algorithm that is benefiting somebody I define a priori. So that's the idea. What's the approach that I'm going to take? Well, it's sort of a three-step approach. The first part is to start with an appropriate model. Again, trying to attack this problem for any general graph, any real graph out there is virtually impossible, so we had to start somewhere. So we needed an appropriate random graph model to start working on. That I need to thank Remco for a conversation we had a couple of years ago, who gave me the idea of which one would be the right model. The second step is to show that we can analyze a rank on this kind of model by something that is called the stochastic fixed point equation. And that has some history by now at this point, and I'll talk a little bit more about that, but that's basically it was Nelly Lidbeck's idea back in 2006, I think, or probably before that. And it's a very nice idea, which now we're working in the process of formalizing and making it rigorous. And the third step is once we have an approximation, an object, a mathematical object that we can actually analyze, let's see what we can say, what the theory says. Curiously enough, step 3 is how I started. Step 3 is pretty much done. It took a few years, but we can say a lot of things about what the limit is going to do. Part 2 was step number 1. We had to come up with a model. And step 2 is basically what I'm going to be talking about today, and the part that still needs a little bit of extra work. So that said, let me go back to a concrete example. Just as I said, it's not that I want you to think only about the World Wide Web, but it's easier to follow my talk if we just think about somebody in specific. So let's talk about the World Wide Web graph. This is not the internet. This is the web pages. So it's a directed graph. Web pages are the nodes, and the links are the edges, so they are directed. And it turns out that Google, for the longest time when they started, they sort of thought like, let's eliminate the possibility of having one page that has a billion links to the same page. Let's say that I have my personal web page, and I have a link to Colombia up here, another one here, another one here, another one here. You know, that contribution should really be glued together. It's not exactly merged, but somehow factored into it, into the way that the algorithm works. So we can think of this graph as actually being simple, just to avoid this potential problem of having too many links to the same page on the same place. What people have been obsessing for now probably 20 years is trying to measure different things on the real internet graph, or the real World Wide Web graph. And what they discovered is that the number of nodes that have more than, let's say, k in links decays as a power law. And as a power law, a pretty heavy one. The way that computer scientists usually write this is with a density rather than the tail. I write the tail because I work with tail, so it's a little bit easier to follow the same parameters. But the idea is here, this is k to minus alpha, with alpha roughly equal to 1.1, which means we're talking about a distribution that has infinite variance. It has finite mean but infinite variance. It turns out that there are several papers out there, especially in the early ages, that measured also the fraction of pages with more than k outlinks, and that also seemed to follow a power law. This, I think, is outdated information. These days, people might argue that it's actually potentially been exponentially tailed on the out degree. Not that it really matters for the work here, but this is sort of the first measurement, and it could either be the way that we're measuring things is different now, or that the structure of the internet has changed, the way that we create outbound links has changed, that this is no longer really that heavy. But this is sort of the original work out there in terms of measuring things. And what's even more interesting, if I'm going to have a model, I'm going to try to match any given specific empirical observations. But what's even more interesting is that not only the in and out degree of these World Web graph follow power laws, but also the ranks themselves. And the ranks here according to one particular algorithm, the famous PageRank algorithm, the one that created Google, or upon which Google was created. And that was rather interesting, and it was interesting because of these coincidences. It's not the same concept of proportionality, but what people observed is that the fraction of pages with a very high rank decayed as a power law, but not only that, it decayed as the same power law as the in degree. Coincidence? No, not really. Moreover, people actually discovered, and this is true, this is practice, that if you ever want to cheat Google, what you have to do is you have to create lots of neighbors that are pointing to your page. Why? Because that inflates your in degree. And why? Because it turns out that the in degree basically is equivalent to what Google does. To this date, it's still true that the in degree is a major contributor to the ranking that Google search engine gives. The thing is now that if one is not careful and you want to do this sort of the old-fashioned way by creating blank pages, you will get caught. And Google will manually reduce the rank of those pages and avoid this from happening. So from what I hear of people who still do this, there's sort of a little bit of testing Google how much you can go in this overinflating of neighbors without being caught. Anyways. So back to the math, I need a random graph model. What kind of random graph model? As I said, Remco gave me the idea that we should try to work on with something simple, something close to so-called configuration model. Configuration model, also known as the pairing model, basically is, in the undirected case, boils down to I have a whole bunch of nodes. To each node I give half edges according to the degree of each node, and then I randomly take a permutation of those and match them. So that's fairly simple. It turns out that this configuration model has very nice properties. The problem was that as of a couple of years ago, there was nothing directed already done there. So we had to sort of make some adjustments and come up with a directed version of the same model. The idea also was, well, because we're going to be doing complicated things on this model, we want to keep as much independence as possible. So one way in which one can construct the undirected configuration model in a fairly straightforward way is you sample IID degrees for each of the nodes. Then you can draw a graph provided that the sum of the degrees is even, and you can always do that, and with probability at least a half this would happen in the case. The problem in the directed version of this is that in order to even draw a graph, you have to have a match between the sum of the in degrees and the out degrees, and that is not so trivial. So there's a lot of work that has to go into that. To explain what the model itself is, let's consider a graph on n nodes with vertices v1 through vn. I'm going to call mi the in degree of node I, basically how many edges are pointing towards the node, and di the out degree of node vi, basically the number of edges pointing out. I call this double sequence, made with the in degrees and out degrees, the bi-degree sequence for the graph. And I have some target distributions that I want to hit as precisely as possible. Whatever it is that computer scientists have measured, I would like to at least be able to capture that. In some sense, think about this as a mean, the first order approximation to something. If we're going to try to match anything, let's start with the basic. Let's try to match the degree distribution. So correlations and other things that one can think of, we're going to leave for later. Let's just be happy with the bare minimum. Under what circumstances can I build this model? Well, very mild ones. Basically, all we need is that they're fairly well behaved in the sense that they can be bounded from above by a power tail. Here, for the purposes of this talk only, I'm going to assume that the indices of these power laws are greater or equal than 2, which basically is essentially the same as asking the distributions eventually to have finite variance. In general, the construction, this part of the model can be done with only finite mean. So I don't need that, but for the results that we'll be presenting today, we will ask that the distributions have finite variance. How do we build the bi-degree sequence that is going to have all these nice properties? Well, I'm going to fix some parameter delta 0 is more than 1/2. In the general case where there's only finite mean, this is going to be the minimum of the 1/2, 1 over alpha, and 1 over beta, basically. So it's the large deviations regime for depending on whether there's finite variance, square root, or if there's infinite variance but finite mean, then we have the 1 over alpha. So there's a little more complicated, but the same thing holds, basically. We're going to sample the in degrees from a MID sequence having the distribution that we're trying to hit. And the same thing for the out degree. We can accommodate some kind of dependence, so I could sample this as IID pairs. But for the purposes of the talk, we can assume that they're also independent of each other. It doesn't really matter. This is the sum of the in degrees. This is the sum of the out degrees. As I said before, in order to be able to draw a graph, the bare minimum is that these two sums have to be the same, which when n gets large, when the number of nodes gets large, happens with probability 0. So that doesn't sound very good. In the case of the undirected graph, it happens with probability roughly 1/2, which is pretty good. In the case of the directed graph, it doesn't. So we need to force them to match. How do we do that? Well, we look at the natural CLT deviation range. So if the difference is smaller than square root of n in this case, it would be the corresponding stable law for the finite mean but infinite variance cases. Then all I have to do is add extra degrees to whichever is smaller. Always add, never subtract, so that I can do this randomly by choosing uniformly at random from who is going to get the extra degrees. This condition is also guaranteeing that no node will get two extra ones, so at most one. And this is basically the way that we're doing it to keep as much of the independence structure as we can possibly can. It turns out to be the right way. Now I'm going to construct the in degree and out degree sequences according to these formulas. So this is the original distribution, and this is potentially 0, 1, depending on whether that node had to be added. We had to add 1 to that number. So these taus and kais are just zeros or ones, mostly zeros. There's only a total of this number of ones. Yes?
Does the data suggest that the in degree and out degree are independent?
Well, I'm sampling them here independently, right?
Assuming them. The data suggests that that's true.
No, the data suggests that there might be some dependence between gamma 1 and psi 1. But that we can accommodate. So, yes, that's not an issue for this construction. It's just a little bit simpler to work this way. Yeah, so that's not really a problem. Now, of course, now that we have this construction and we have a bi-degree sequence, this bi-degree sequence is not IID anymore. It's dependent, obviously. They're both dependent. Why? Because they have the same sum. So. Now we have this bi-degree sequence, and we do the standard pairing. So basically, we can think of drawing the nodes like this. To each one, we draw its out degrees. And its in degrees. And then take a uniform permutation of the two and match them. That's basically our thing. We can do it one at a time in traditional sense, or we can do them all in one permutation. They're both equivalent ways of doing so. So what do we obtain at the end of this procedure? We obtain a multigraph. Why? Why not just a graph? Because there might be some nodes that end up with self-loops, like this guy connecting to one of its own. And there could be multiple edges in the same direction. And of course, some of the configurations are going to be more likely than others, depending on how many configurations are there that have certain number of self-loops for one node and that kind of thing. So you can see how they're not going to be uniformly sampled unless we restrict our attention to the case of the graph being simple. In that case, we basically have a way of generating a uniformly chosen simple graph having n and d as this bi-degree sequence. So some of the properties of this random graph model that I just described is, well, first of all, the way that I constructed the bi-degree sequence gives us that the sequence will be graphical, meaning that one can even construct a simple graph. And not any sequence would it be possible to construct it. You can think of one node having way too many more than everybody else, then there's no way we can avoid drawing a self-loop at some point. So this bi-degree sequence does not have that problem. With probability that converges to 1 as the number of nodes goes to infinity, it will be graphical. Moreover, the probability of the resulting graph after the random pairing being simple is bounded away from 0, provided that we have finite variance. So this is a very nice model that's basically not too far away from just sampling uniformly independent degree sequence according to the target distribution, which is the nice thing about it. And of course, now the distribution of the in degree and out degree is not a priori F and G, so there's a little extra work that one needs to show that whatever manipulations we've done, which is first adding extra degrees and second conditioning the graph to having been simple, that did not destroy somehow the limiting distributions, and the thing is it doesn't. So that we showed, and we have a little short paper that says exactly that. So back to the ranking. Now we have a model. Let's see how we're going to analyze the ranking algorithm on this model. This is, if you look up on Wikipedia what PageRank does, this is basically the system of equations satisfied by PageRank. PageRank is Google's original algorithm, trademarked by Page and Brin. This D is called the damping factor, so a number between 0 and 1. And for all of us here probabilists, maybe it's more familiar to think about this not as a big set of linear equations, but rather as a random walk. It's a random walk on a graph where a person is flipping a coin with probability of landing head D. Every time it lands heads, he chooses any of the links on that page where he currently is to follow. And with probability of tails, he will choose among all the web pages on the internet. So that's N here. So what is PageRank? PageRank is nothing but the steady state distribution of this random walk. In other words, it's measuring the long run proportion of time that these random surfer would spend on any given page. In other words, it's a measure of popularity, how popular those pages are. What people do to obtain significant random variables is to multiply this whole thing by n. And now, because n is in the millions or billions, then this is now essentially a quantity that is unbounded, has unbounded support, and we call this the scale-free rank. In linear algebra terms, this is nothing but a set of linear equations with some weight matrix M. When is that going to converge? Well, when this M has a maximum eigenvalue strictly smaller than 1, as we all know. So what do we do with this complicated graph structure? Well, we start looking at what would happen if we choose randomly one node in this graph. So I choose randomly one node, and I start exploring the graph. These pink arrows are the out degrees of the nodes that I explore. I only drew a few so that the graph wouldn't be too crowded, but you can think of each of the nodes on this graph having some certain number of outbound links. And what's going to happen is that I start walking down, and it's going to take a while before I encounter a node that I had already visited before. We call this the local tree-like structure. The key thing is that this has to hold for at least, a constant times log of n. If there's any chance of making what my theory work, then it has to be on a graph of this type, and of course the model I just described has exactly that property. Among many other models, including in the undirected case, most random graph models would have this property, by the way. So it's not rare, it's not realistic, but among synthetic models, almost any model will have it. So how is that connected to a stochastic fixed point equation? Well, power iterations. If it's a fixed point equation in the matrix notation, we know that the procedure of iterating that fixed point equation many times will eventually lead to the solution of the ranks, assuming, of course, that the maximum eigenvalue of m is smaller than 1. As we know, if there is going to be convergence, it's going to be geometrically fast, which means that it's not unreasonable to assume that only after a finitely many iterations we'll already be very, very close. So if this tree-like structure lasts long enough that m to the k is small enough or negligible with respect to everything else, then we actually have hope of disregarding the entire complicated link structure of the graph, the connections. Why? Because if I'm only going to be looking at the original node, the one on the top of the tree, and I get there and I can compute its rank essentially with k iterations, and I haven't gotten to the point where the tree structure disappears, then it's the same thing as if I had just computed its rank on a tree. That idea was first published in 2007 by Nelly Lidbeck and her student Jana and a collaborator at Yahoo. And the idea was the following. Well, if I look at a randomly chosen node, what am I going to see? I'm going to see that constant plus the weighted sum. And let's forget about where that sum is being computed. And let's just make it a sum of a random number of terms where the number of terms has the in-degree distribution. Here, the d that appears is no longer the one over here. It's not just the out degree. Why? Because I'm biasing my observations, because I'm only counting those nodes that do have a connection towards the one that I sample. So it's actually something called the effective out degree distribution, also related to something people in graph theory call the size bias distribution, right? Because I know that it has a connection. So this is the main idea of the approximation. What is it doing? It's disregarding the links between the graph. It's basically computing the rank on a tree. So is that enough? Well, if n is the number of nodes in the graph, n and d are the random variables chosen according to the in degree and the effective out degrees, and this Rn in boldface is the rank, this is a vector of size billions or millions or whatever it is, then what our main result says is that provided that this parameter that I'm going to call rho is more than 1/2, then we do have convergence to a finite random variable, convergence in distribution, where that random variable is a solution to this fixed point equation. Now, I'm firmly convinced that this result holds up to rho up to 1, strictly smaller than 1. That's the hard part. This is the easy part. So I'm afraid I'm not completely done yet, but the idea is that this should be fairly smooth on all the values. By the way, rho equals 1 is unstable, so that is not an interesting case. And anything bigger than 1 would be unstable too. So now we have the stochastic fixed point approximation. How we get there? Let me just briefly mention the steps. The first step is to show that we only need finitely many iterations to compute that first component of the vector. In other words, we need control over these matrix to the k. So we want this to go uniformly to 0 fast enough for some function k, which is growing as a function of n. And provided that happens, if I call R1 the first component of that vector, that's my randomly chosen node, then what we obtain is that R1 and R1 computed only with k iterations of the fixed point equation goes to 0. So in other words, I'm okay with just using only finitely many iterations. The second step is to go from finitely many iterations to the coupling with a tree. The idea, a standard idea in random graph theory, is to construct the graph and a corresponding tree simultaneously, as long as I can, until that first time that we sample the node that we have already visited. So here, the distributions that we're using for the coupled tree are actually based on the in and out degrees, or if I want to include more general weights on the node attributes themselves, they're based on the graph itself, which means that these are random distributions for both the in degree, out degree, and whatever other weights that we might want to add into the picture. So now if I call R and K denote the rank of the root node of this tree after k iterations, then what I have is that the actual rank of that first node on the graph and the one computed on the coupled tree goes to 0. And the third step is going from the solution of after finitely many iterations on the coupled tree to a random variable R that no longer has any randomness in it, no dependence on n. So here the limiting distribution is the limiting random variable is R, where R is a solution to this fixed point equation. This would be the trivial part considering all the work on branching process that there is today if it wasn't for the fact that all the distribution is random. So that, again, as I was telling Remco, took another few months of my time to get there, this last step. But yeah, that part is done. And like, as I said before, I strongly conjecture that my 1/2 is completely arbitrary and due to the fact that I haven't had the time to get all the way through, but that it should be all the way to 1. What else do we want to say about this? Well, once we have the fixed point equations, as I said, general weights, not necessarily page rank, we can toss in other pieces of information that we might have, and we can consider this linear fixed point equation, and we'll have different behaviors. I'll talk about that in a second. And more importantly, this approach is not limited to linear recursions. We can also use it to max plus recursions of other types. So it opens the door to designing different kinds of algorithms where using the coupling, we can show the stability and also the limiting behavior. So these are other interesting recursions. This one is a generalization of the maximum recursion, known to everybody here as the Lindley recursion. In other words, the single server queue. Why? If you don't see it, make n equals 1 and take x, this is just the logarithm of Lindley's recursion when q is equal to 1. And again, as my friend Predrag would say, when we discovered finally after several years of working with these subjects, there is a queuing connection. So, as he would say, all paths lead to queuing. The queuing system that follows this recursion, it's a funny kind of multi-server system where you have many servers in parallel, you have jobs that get split into pieces, and those pieces get sent randomly to the different servers. The catch is that at the moment that they reach the front of the corresponding queues, they need to wait for all the other pieces to be at the front. Once they're all synchronized, it gets processed. So this sort of synchronized queue actually can be analyzed via this generalized Lindley recursion.
And other stuff has to wait behind them until they get synchronized.
Yes. Yeah. It's I don't know exactly. I think there might be some situations in computer science where this is required because there might be needs for communicating between parts. So they all have to be processed simultaneously. And this generalized linear recursion precisely has corresponds to the steady state behavior of this queue. Just quickly, as I said, this is all work. We know a lot about the limiting distribution. And the beauty of it is that it's heavy tail almost always. It's nice to analyze under 3 different scenarios the existence of a certain root to this equation. If the sum of the weights, or equivalently the in degree, is heavy-tailed, or if the Q is heavy-tailed, in any of those cases, the limit is going to be very well understood. We have exact asymptotics for it. We can say a lot about it. Just to explain what I said before about PageRank, this is the reason why you can cheat Google. So in large deviations, we know that the sum of the weights for the actual case of PageRank decomposes into a constant times the probability of the distribution of the in degree. Moreover, if we look at the proof, it turns out that the probability of a page being highly ranked can be decomposed into 2 pieces. One, you have a very important neighbor. So if somebody with a very high rank points to your page, you will automatically have a very high rank. And the other is you just have lots of neighbors. Typical neighbors. They don't have to have high ranks. You just have many of them. This is how people have been cheating Google for 15 years now. In general, for the future, we want to use those weights to generate other algorithms going beyond PageRank. PageRank only uses 2 things of the information that is available: in degrees and out degrees. That's it. But we have a lot more than that. As I said, I gave you a few examples at the beginning. What if we use those to obtain different kinds of ranking? Also, if we want to be more robust to manipulation, just consider the case where those weights are in that first scenario that I mentioned. In that case, this is not possible anymore. It's not easy to tamper with this as a user. Other recursions will lead to new algorithms, so we have a whole door opens of new things to do to rank information. Again, in terms of the future, I need to finish my proof all the way to rho equals 1. The idea is in my mind that maybe it's not the configuration model that's making this work. It could just be the local tree-like behavior. That's an open question that yet to be explored. And we, of course, want to do a lot of numerical work in terms of how do we validate this. First, with the model we talked about. Second, with other synthetic graphs, for example, famous preferential attachment graphs. Third, let's look at real graphs. Real graphs do not have the local tree-like property. But these are power laws. That index alpha is going to prevail. How much? That's a question yet to determine. And with that, I want to thank you for your attention.
Thank you very much. Comment, please. Please.
So you did this power iteration, which converges as k goes to infinity, but it depends on how big k is relative to n.
Yeah.
And in the tree, you can go about log n steps. So does the power iteration converge faster than log n steps?
As I said, that's why I have the easy case of rho smaller than 1/2, because when rho is smaller than 1/2, that rho is a contraction factor. It's so fast that it's enough. That's why I call that the cheating case. As I said, the other parts of the steps 1 and 3, took a long time. So that second step, which is the important one, I have the easy one that took me all of like maybe a week to do. Yeah, that's the hard part. With drawers sufficiently small, yes. But it's going to require extra work to go beyond that because that's the tricky thing.
Where are you relying on the variance of your in and out degree to be finite?
Just in the construction of the simple graph?
No, the coupling. When does the coupling fail? So the first time that you would sample that node on the bottom, the parameter, so it's that C, which in this case is 1/2, right? 1/2 log of n. When you have infinite variance, goes to, remember that parameter that I mentioned here? Yes, here. So delta, I said here in the general case, this is the minimum of 1/2, 1 minus 1 over alpha, 1 minus 1 over beta. That's where. And that's going to play a very important role in how far we can go. So in the general infinite mean case, I don't expect the coupling to be long enough. What I do expect is that even though the coupling does not hold, this is still a geometric, these are terms that are decreasing geometrically fast. So how many nodes after I find the first one, maybe it happens fast. But still, having found that, it's not going to add too much. All the contribution of that one is still going to be negligible, at least in my mind, with respect to the overall picture. So it doesn't matter. It's just going to require a lot more than union bounds to show it.
At first, I love this word. At first sight, I'd be terrified of variance. I mean, trying to estimate such a high-dimensional vector sounds impossible. And my conjecture would be you're safe because you don't really care about the exact values. You just care about the ordering. And I mean, is there any way to make that precise, or is there an issue with variance with the algorithm? You know.
For drawing the graph, the graph itself, no. The variance. No, there isn't. Actually, this. We're going to need the finite mean. I have the impression that's going to show up. Actually, no, because all of this row, in the more general weighted branching process case, is actually assumed where n could be infinite. It has to do with how fast the weights are going to 0. So it has to do with these functional, the sum of the weights to the alpha, actually. Do I have it somewhere? Yeah, this guy. So in general, this guy over here is going to still have an expected value strictly smaller than 1 for some parameter alpha. And that's all that matters. So even if n was infinite, that's something that the theory accommodates. So no, I don't expect it to be an issue. It's going to be an issue with the coupling. That I'm sure. That I know because that's why I haven't been able to finish this. And I really haven't spent that much time, to be honest. But not on that part.
Does the assumption ensure that the fixed point equation is a unique solution?
That's a beautiful question. As a matter of fact, it's not unique. This is coming from a whole branch of theory that now we call weighted branching process theory, and there's a fair enough community of people who look at this. That equation does not have a unique solution in general. It does have what we call a unique endogenous solution, and that happens to be the solution that we are interested in. And it's unique in the sense that if one starts iterating the fixed point equation, starting with a reasonable initial value, you will always converge to the solution that I'm analyzing, always. If you start iterating the fixed point equation with a certain stable law distribution, then there are other fixed points of the equation that have been fully characterized or almost fully characterized by now. But from an engineering perspective or an applied perspective, those other solutions don't matter. So no, that's not unique, but it's the only one that matters for this purpose. And in that sense, it is the only one.
Thanks again for speaker.